We found that we could factor a difference of squares, but that a sum of squares was prime. What about a sum of cubes? We know how to factor a difference of cubes. To try to feel our way toward a way to factor a sum of cubes, we might try just replacing our second number in our difference of cubes by something that's somehow negative. Right, so if we have a cubed minus b cubed, replacing b with some negative c, we have a cubed minus negative c cubed. So that'll be a cubed, negative c, so a negative times a third negative, that comes out negative. So we have a cubed minus negative c cubed. That's a cubed plus c cubed. Oh, we like that. That is a sum of cubes. I think that we're going to get a way to factor that. The difference of cubes factors as a minus b times a squared plus ab plus b squared. Let's replace the b by a negative c and see what happens. Well, I have a minus negative c. That's going to be a plus c. And then a squared. A times negative c is a negative a times c. Negative c, when I square it, the negatives cancel out, and I'll get a positive c squared. So this is a new form, right? This is a different form from our difference of cubes. This is now a sum of cubes. And when we factor, our first factor will be a plus some c. And then our second factor will have subtraction in the second term. So how do we recognize a sum of cubes? Well, the coefficients of each term will be perfect cube numbers. The powers of variables are multiples of 3. So each term is a perfect cube monomial. And then both terms are positive. Of course, if we have two perfect cube monomials and they're both negative, we can factor out -1, and then we'll have a sum of cubes. So both positive is a sum of cubes, both negative, actually a sum of cubes in disguise. Let's see a couple of examples of sums of cubes that we can factor. So I've got 8x to the third plus 1. Well, 8x to the third, 8 is 2 to the third, x to the third is just x to the third. So that's 2x all to the third power, plus, of course, 1 to any power is just 1. So this is 1 to the third power. This is a sum of cubes with big A is 2x and big B is 1. So this factors. First factor is a plus b, 2x plus 1. Second factor, I'll have a squared, so 2x squared, minus a times b, so 2x times 1, plus b squared, so 1 squared. And then simplifying the second term, 2x plus 1 times 4x squared minus 2x plus 1. It can be challenging to keep track of where the negative sign is in the sum of cubes. If you're unsure, you can multiply out to check. So We had a sum of cubes x cubed plus 1. We can have a sum of cubes x to the 6th plus y to the 6th. X to the 6th is x squared to the 3rd. Y to the 6th is y squared to the 3rd. So this is a sum of cubes with a is x squared and b is y squared. So our first factor is a plus b, x squared plus y squared. Our second factor, we have a squared, so x squared squared, minus ab, so minus x squared times y squared, plus b squared, so y squared squared. So x squared plus y squared times x to the 4th minus x squared y squared plus y to the 4th. Now, the keen observer might be noticing that this is a sum of squares. So this is x to the 3rd squared plus y to the 3rd squared. And you'll recall we said that a sum of squares can never be factored as a product of two binomials. Well, that's okay, because this is a trinomial. So that doesn't violate what we said about the sum of squares. We said the sum of squares is usually prime if we have another special form that we can slot it into, like a sum of cubes, then we're fine. Of course, this guy now is definitely prime. And it turns out that this guy is prime also. So we got a little ways, but not very far by thinking of this as a sum of cubes. So difference of squares, difference of cubes, we can generalize that for any power. For any odd power, we can generalize what we did to get from the difference of cubes to the sum of cubes. For even powers, the sum remains prime, unless there's some other trick. Right? So unless we can see that sum as something else, as in the previous example.